Okay, so we went, if you notice, we skipped 2.3 before on velocity, acceleration, and doing second derivatives now, which is just taking the derivative of the first derivative. And sorry, I'm just going to excuse myself and say, just before I started this video, I noticed I had the hiccups. So I took a drink of water. We'll see how it goes, but depending on how bad it is, I might have to stop the video a little earlier and just continue on after once I can get rid of these things. So, okay, so 2.3, which is the last, probably the last section of chapter 2 that I will do. Let's talk about displacement, the definition, velocity, and then we'll talk about acceleration on the second page. So displacement, it measures how far an object is from its starting point. And the common notation would be S of t. So just as an example here, we live in London, or you live around London. So let's say I'm driving from London to Toronto. I drove all the way to Toronto. And then, I'm driving back to London, but I only get as far as Woodstock, let's say. Displacement would only measure how far away the object, the car, is from its starting point. So when I'm in Woodstock, the displacement is going to measure how far away I am from Woodstock to London. It doesn't care that I've gone to Toronto or not, just where am I in Woodstock and how far am I away from my original point, which was London. Whereas the distance, right, would measure how far I've traveled. So the distance would measure from London to Toronto and then from Toronto to Woodstock, for example, okay? And distance would be, just add this in here, labeled as a D for distance. So that's why we don't use D for displacement. That's why we're going to label displacement as S of t. Okay, so then moving up, velocity would be our speed, right? So speed measures how fast an object is moving, and it doesn't consider the direction. So what is my speed if I'm moving horizontally left or right? Or what is my speed if I was to jump out of a plane, right? And we're talking vertically up and down. What is my speed as I'm approaching, heading back to Earth? Whereas velocity measures how fast an object is moving, but it also keeps note of the direction of the movement, which speed does not. In order to get the velocity, we're just taking the derivative of the displacement function. So if the displacement function is s of t, right, then s prime of t would be the velocity. And another way to write s prime of t, that would be equal to, we are going to use v for velocity, v of t. Those would be equal to each other. So we are going to be talking about movement here in terms of the direction of movement for velocity, right? So here, let's talk about the direction. So if I have horizontal motion, so we were talking about left and right. So for the displacement function, s of t, if an object is moving along a horizontal line, so moving left or right, we want to say, I would write that down. If the velocity of the object is referred to as, again, velocity, v of t, or velocity of the same thing as taking the derivative of the displacement function, s prime of t. If the velocity, or if f prime of t, happens to be greater than 0, then the object is moving to the right, or we say that as advancing. So graphically, the tangent lines will be positive. Okay, tangent lines will be positive. If the velocity is less than 0, then the object is moving to the left, then we say that it's actually retreating in terms of motion. And graphically, the tangent lines would be negative on the displacement function along the curve. And if the velocity was equaling 0, so if your movement was 0, then the object is stationary, you're not moving, right? So then graphically, the tangent lines would be horizontal on your original displacement function. Tangent lines would be horizontal. Okay, what if we're talking about vertical motion? So here, let's say we're talking about a lot of this. Let's say if you think back to grade 10 academic, what did we do in grade 10 that we didn't do in grade 9? Quadratics, right? So if I'm talking about throwing an object up in the air and then it comes back down due to gravity, then it's following a quadratic. So we can just kind of write that in here. So let's say an example would be a quadratic function here. Now I'm not necessarily, you know, it might start at the ground, or it might be something that starts up here and comes back down, but it goes up and then comes back down following a quadratic that opens down, let's say, right? So for the height, now we're just calling the height here f of t, but we could be calling the height h of t as well, right, for height. If the object is moving vertically, then the velocity of the object is referred to as, the velocity would just be the derivative, right, of the original function. The same as horizontal, we're taking the derivative of the original function. If that derivative is greater than 0, if it's positive, then the object is moving up. Then we know that it's going in this direction, it's moving up. Graphically, the tangent lines are positive, right? So any point I would have along that curve, if I was to draw a tangent line, that would be positive. If velocity is less than 0, so if the first derivative is less than 0, then I know the object is moving downwards. I would be on, let's say, the right-hand side here of the quadratic. And if I was to have points here and draw tangent lines, those tangent lines would be negative. And same as before, if the velocity was 0, the object is going to be stationary, which means it's not moving. So there's no speed, right? There's no velocity. And the tangent lines would also be horizontal. And this is also occurring, right, where the graph is at its maximum or minimum point. So for example, here at the very top of the vertex of the quadratic, a tangent line, if I were to draw, would be horizontal. The slope would be 0, but that's happening at a maximum point. Or if it was opening up, it'd be happening at a minimum point as well, right? Okay, let's look at acceleration. Acceleration will determine whether the object is speeding up or slowing down. So we're not just talking about motion, but we're talking about, you know, let's say if you were driving 50 in the city, 50 kilometers an hour in the car. Speeding up would be pushing the pedal down, the gas pedal down, right? It's not just talking about the fact that you're moving, but that you're speeding up, acceleration. Or the opposite of acceleration and slowing down would be slamming on the brakes, right? This is getting the second derivative of the original function. Or the velocity function is the first derivative, right? The velocity function here, v prime of t, or sorry, v of, I won't look at this one. Let's look at this one here. The velocity function, right, is getting the first derivative, s prime of t. So then if I was to get the second derivative, which is just the derivative of the first derivative, that would be my acceleration. So common notation, I can use a for acceleration. So acceleration function is equal to taking the velocity function and taking the derivative of it, because that's already a first derivative, the velocity, right? Or s double prime of t, we could call it. So just getting the second derivative of the displacement function, right? So these kind of go hand in hand. So if the acceleration is greater than 0, the velocity is increasing. So therefore, if it's increasing, the tangent lines are positive, right? If the acceleration happens to be less than 0, the velocity, my speed, if you will, is kind of decreasing, right? So then my tangent lines are negative. And if my acceleration is 0, it doesn't mean that I don't have speed. It means that my velocity, my movement is constant. So I'm just going 50 down the road without speeding up or slowing down. I'm on cruise control then, if you will, in the car. Your speed is constant. And then your tangent lines will be horizontal. So just be careful with that one. If your acceleration is 0, you still have movement, right? It's just that the movement is constant. You are not speeding up or slowing down. So an object speeds up when the velocity and acceleration have the same signs. So if my acceleration is positive and my velocity is positive, then it means that I'm speeding up. An object would be slowing down if my velocity and acceleration function have opposite signs. And we'll go through examples of that so that you understand. So because of gravity here. So let's say an object is, let's say your velocity is speeding up, but then your acceleration is slowing down, right? So if your acceleration is slowing down, this could be due to gravity as you're getting up to the maximum point of a quadratic, right? Then you would be slowing down. Then that is telling us that we would have opposite signs, and that's helping us understand that I would be slowing down, or the opposite of acceleration. So other notations we could have here for the second derivative, because this is the first time that we're seeing it. So we have our original function f of x. The first derivative is obviously f prime of x, or f prime, or dy dx, we say. Or technically, I'm just thinking here, we also would have, you know, I know this says f of x, but we've also written it as y prime. The second derivative is the same thing. So f double prime of x, f double prime, or d squared y over dx squared, right? Or y double prime. And again, we don't really use this Leibniz's notation very often here for the second derivative. You'll probably see one of the other ones. So it's called f double prime. Let's just do examples first before we get into word problems of simply just getting the second derivative of equations, right? Of the original function. So let's look at here. Find y double prime. So I can't jump right to that answer. What I need to do, so it's asking us to get the second, just to write out here, it's asking us to get the second derivative. So if this is our original, I have to get the first derivative first, right? So y prime, which is what we're used to, that should be relatively easy. 4 times 4, 16x cubed minus 2. This is my, just to point out here, first derivative, right? This is what we've been doing. Now, using that, I get my second derivative. So now I'm going to get y double prime, which is again 3 times 16. So 15, 30, 45, plus the extra 3, so 48. X, one less, squared, and that would be minus 0, right? So just to guess, I mean, we should know that, but just to write that out, it's going to end up being 48x squared is my y double prime. And again, that would be my second derivative. And that's all there is to it. Let's try another example. Now, this was just a question with 3 terms in it. What if I was multiplying here? So again, this is like f of x multiplied by g of x f of x multiplied by g of x, right? Originally, so 2 brackets multiplied by each other. So to get the derivative, I get the derivative of the first times the second, and then I add, like product rule here, right? The derivative of the second times the first. So just to write that out for y prime I'm talking about, we would have f prime of x multiplied by g of x. And then again, don't forget we're adding, and then we're taking the derivative of the second, multiplying it by the first. You could put a circle in there if you wanted to. So let's follow that. Y prime would be, again, getting the derivative of the first. The derivative of the first would be 3 times 2, 6x minus 8. And then multiplied by the second, so multiplied by 6 plus 5x. And then our addition sign, the derivative of the second. So the derivative of the second, if you see here, is actually only 5, right? Multiplied by copying out the first term. So 3x squared minus 8x minus 7. Then here, to go farther expanding two binomials here would be, just to write out, I'm going to be using FOIL here, right? So that would be 36x plus 30x squared minus 48 minus 40x. And then again, distributive property on this side. So I have a bunch of like terms here that I can now, hopefully I can fit everything in here. So I have 36x plus 30x squared minus 48 minus 40x plus 15x squared minus 40x minus 35. Good, I can fit it all in. So again, like terms here, use your different colors. I have an x, I have an x, I have an x. I have an x squared, and the sign goes with it, and I have an x squared, and then the constants. So that's going to condense to what? Let's do our squareds first. So y prime would be 30x squared plus 15x squared, so 45x squared. Cross out. Then my x's, 36 minus 40 would be negative 4 minus another 40. So that would be negative 44x. Cross out. And then again, 48 floors below ground, and I'm going down another 35, would be negative 83. Now this is my first derivative, right? Simplified. This was the first derivative too. Sorry, this line here, my green line. But this is the first derivative simplified. Obviously, this looks way better than the line above. Now, I haven't got the second derivative yet, like it asked. So to get y double prime, I'm just getting the derivative pretending this was my line here. So doubling 45 would be 90x, bringing that 1 in front, minus 44, x to the exponent of 0. The x is gone, and that's just 0. So 90x minus 44, and this is our second derivative. So if we go into the second example here, hopefully I can fit it in down here. Determine the velocity and acceleration. So velocity is asking for the first derivative. So let's just say s prime of t. And the acceleration is technically asking for s double prime of t, right? Or the derivative of the velocity function for this function s of t. So s of t equals 6 plus 3t squared minus 5t cubed. So the velocity would be s prime of t is, the 6 is 0. So this 3 times 2 is 6t minus 15t squared. Now you could leave it like that, but I know that we usually have the t squared first, the highest exponent first. And another way to write s prime of t would be the first derivative is the velocity function, right? So let's write that out. This is, just so we know, the velocity function. So velocity is the first derivative. So I could write that as v of t equaling negative 15t squared plus 6t if I wanted to change the order up, right? Now to get second derivative, s double prime of t, I'm simply just getting the derivative of the velocity function, which is the same thing as the s prime of t, right? So the 2 in front, negative 30t plus 6 is my second derivative. So this is my acceleration function. And another way to write acceleration, sorry, hopefully you can see this here, is just, again, a of t is negative 30t, or just 6 minus 30t. If you didn't rearrange it, it would be 6 minus 30t. So what did it ask for? Determine the velocity function. Got it. Just ask for the function. And the acceleration function for this positive function, just s of t. So that's it. We're done. Okay, let's look at number 3 here. Again, I'll start you off. I'll let you maybe think about the first couple, and then we can take that up. So completely different question, right? The height of a rock, so sounds a lot like your quadratic grade 10 questions, right? The height of a rock, h of t, we're calling it, It's in meters above the water, and time is in seconds, can be modeled by this equation. Looks very similar. You know, it's a quadratic, it's squared. H of t equals negative 4.9 t squared plus 12t plus 15. What is the initial velocity of the rock? So for the initial velocity, we're going to get velocity. Velocity in itself is just the first derivative, right? So we're going to get h prime of t. And then initial velocity would mean initially time is 0, right? So we're just going to sub 0 in for t. Then b, I'll let you, let's, like I said, have you guys work on the first 2 or so. Then we'll start taking it up. When does the rock reach its maximum height? And what is the maximum height? So that would have been your vertex in grade 10, right? What's the time when it reaches the maximum height? And what is the maximum height? It's asking for the point. It's asking for both the x, the horizontal axis, and the vertical axis number, right? So this happens at the vertex. At the vertex, if you remember, the tangent line is horizontal at the vertex. When the tangent line is horizontal, my velocity is 0. So I have my velocity function from A, make the velocity equal to 0, not time, but the velocity equal to 0, and that will answer you for time. Once I have that time, sub it in to your original function for t, and then you would get your height for that value. So again, just starting there, let's say, I think that's enough for you to remember without writing down. And again, you can continue on if you want to. Give that a shot, and then we'll take those up.